Today I'm going to talk about an interesting paradox in probability called the St. Petersburg paradox. The St. Petersburg paradox concerns games of chance in which participants may win money. And the question that we're asking in every case is how much money as a participant should I be prepared to pay as a stake to play this game? Just a word of warning, in a casino, the answer to this question will always be less money than they're going to make you pay to play the game. It's not a good idea to gamble in a casino because you will lose money. And if you want to lose your money, then there are much better ideas for what you could do with it. So this first game, which we're going to think of as an example, concerns tossing a coin. So we toss a coin and either we get heads, and if we get heads then we win, and we win $2. Or we get tails. If you get tails you lose and you get no dollars. So the question is, how much money should I be prepared to pay as a stake to play this game? So in statistics we have this idea called an expected value, which you could think of as the mean amount of money that you're going to win. So in this particular case, if the coin is fair, then we can say X is a random variable which represents the amount of money that we win. So the probability that X equals 0 is just the probability that we toss a tail, and that's a half, and the probability that X equals 2 is a half as well, and X cannot take on any other value, because we can only get a head or a tail, assuming that the coin doesn't land on its side or something. So then we consider the expected value, which we can calculate with this sum. So we add up over all possible outcomes, little x, the probability that our random variable big X is equal to little x. This is the general formula for the expected value. So in this case, we get 0 times the probability that big X equals 0, and then add 2 times the probability that little x equals 2. And that's equal to, so the first part is just 0, and the second part is 2 times a half, which is 1. So the expected amount of money that we win is $1, and there's a theorem called the law of large numbers, which tells us that in the long term we will lose money if the stake that we place is greater than the expected value. We'll win money if the stake is less than the expected amount we will win, and on average we will break even if the stake that we play is exactly $1. So we could say $1 is a fair stake. Okay, so in this next game we're also tossing coins, but the rules are a little more complicated. So if we toss a tail, then we stop. But if we toss a head, then we carry on tossing until we get a tail, and then we stop. So that's the rules of this next game, which is the one that the St. Petersburg paradox concerns. So as some examples of possible outcomes, we have these. So we might get just a tail, we might get head, 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 tail, we might get head, head, tail, and then I added in just the tail again to reflect the fact that about half the time you're going to get just a tail and then stop. So the rules of the game now are that we start off with $1, and then for every time that we toss the coin, we double that amount. So we get $2 if we only toss the coin once and get a tail straight away. If we toss the coin 4 times, we get $16. If we toss the coin 3 times, we get $8. So it will always be 2 to the power of the number of times that we toss the coin. And the question is, how much money should I pay as a stake to play this game? So if tail appears for the first time on toss number n, then the prize is 2 to the power of n dollars. So what would be a fair stake for this game? Well, let's have a think about the expected values again. So the probability that x equals 2 to the power of n is the probability that the first tail appears on toss number n. And that's 1 over 2 to the n, because because we have to get head, 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 and then tail, right? So that's a half probability for each, and we multiply them together. So little x times the probability that big X equals to little x is equal to 1 if x is a power of 2 and 0 otherwise, because we can only get a power of 2. I should say a power of 2 to the power of some positive integer, because we can't get $1 either, which is technically a power of 2. Now, the expected value of x is equal to the sum over all possible outcomes little x of little x times the probability that big X is equal to little x. So this is equal to 2 times a half plus 4 times a quarter plus 8 times an eighth plus off to infinity. Right, because the probability that big X equals little x will be 1 over 2 to the n, and then the price in dollars is 2 to the n. But this is equal to 1 plus 1 plus 1 plus 1 plus 1. Seems to go on forever. So that looks like the expected value of the amount that we win should be infinity. And so any finite amount of money that we pay as a stake will be less than a fair stake. So it will be advantageous for the player in the long term. Obviously, if you pay an infinite amount of money to begin with, you're guaranteed to lose money. But any finite amount of money should be fine. But let's think about this. Would you pay $10 to play this game? What about $20? $100? Or $1,000? I mean, I would hope that just thinking about this, some intuition is telling you I should not be paying $100 and certainly not $1,000 to play this game. So how do we resolve this paradox? Well, one idea is to impose an upper limit on the payout. And in practice, it feels like this should probably happen, right? I mean, let's have a look at this, right? This is information about the economy of the United States. The GDP, so the total of all transactions made within the United States in a given year, is $26.95 trillion. And 2 to the power of 45 is $35.184 trillion. So if I happen to get 44 heads and then a tail, then I should be expecting to get a payout of $35 trillion. But I feel like if that's greater than the GDP of the United States, probably the person I'm making this bet with is not going to have that money. And so I'm not going to actually end up getting that. And so it seems like then a fair stake in practice should certainly be less than $45, because we have to exclude the case where we get more than 44 heads, because they're just not going to be able to honour the deal in that case. Another idea is to have what's called a non-linear utility function. So the basic idea behind this is, if we think about different amounts of money, these all represent different amounts of wealth that a person can have. So Elon Musk has $241 billion. J.K. Rowling has $670 million. To be in the top 2% of people in the United States, you would have $2.47 million. The global median net worth is $8,654. And if you own nothing but a £20 note, then your net worth is $25.21. Now, all of these are roughly 300 times as much as the next one, right? But it seems that having $241 billion is not 300 times better than having $670 million, right? If we were sort of thinking about what the average person would think of these amounts of money, these three on the left would all be in the rich category. This on the right would definitely be in the poor category. And although net worth is a flawed measure, so it might be difficult to say whether this global median is rich, poor, somewhere in the middle, and will depend on the situation that you're in. You I think we can definitely say that the difference between, say, being in the top 2% of the United States and being at the global median is definitely more significant than say the difference between J.K. Rowling and being in the top 2% of the USA. Right? So we can, and certainly, if you weren't convinced by that previous slide, if you were offered a chance to be as rich as Elon Musk, but you only have a 1% chance, and the other 99% of the time you'll have nothing but a £20 note. And then the other option is to have a 100% chance of being as rich as J.K. Rowling, right? Even though the first one has a higher expected value, the second option definitely, I think, would be more appealing to most people. And if it isn't, it's probably because you don't want to be rich rather than because you do. So we could sort of think of this as, like, we could have a graph of sort of diminishing returns, right? So we could have a number that we put on here to represent how happy you are with your situation. And the difference between $0 and $1,000 here is a big difference compared to the difference between, say, $1,000 and $2,000. But we should ask ourselves, can we really put a number on how happy you are, right? We use these emojis. This sort of seems like a bit of a simplistic understanding of things. Well, we do have this theorem in maths called the von Neumann-Morgenstern utility theorem, which says that under certain axioms of rational behavior, we can do this. So there will be some function that we could sort of say represents how happy you are. That you will always be attempting to maximize the expected value of. However, I'd just like to come back to this and highlight this part, right? Certain axioms of rational behavior. If you actually look at what those axioms are, and I may make another video about this, so keep an eye out for that, then I would, so axioms being like assumptions, I would not say that any rational person would have to make these assumptions. So I would say be suspicious of this. But in conclusion then, yeah, assumptions do need to be made for a utility function to exist, with this non-linear utility function idea. And I think perhaps more importantly, the utility function has still got to be bounded. So we can't have like infinite happiness, because if we could, then we could do the same thing, but say, okay, instead of saying the price is 2 to the power of n dollars, it will be some amount of money or some situation. Maybe money can't get you infinitely happy, but something else can. I don't know. But just say we'll replace the price of 2 to the n dollars by some price that will give you 2 to the n utility. And we would have the same problem that we did before. So either way, I think basically the first option is going to be the one that we probably use to resolve this. And thanks for watching.